Directly driven supercharged engines. Let's take a look. On this GSO 480, I should say IGSO 480, we have a directly driven supercharger, which is going to supply actual boost to this engine. The way this works is we have the front of our intake over here. This is our ram air inlet. It is going to travel through this inlet manifold, or what we call a trunk in this case. In most cases, if you have an updraft system like this under the engine, it gets referred to as a trunk. It'll come back up through here. We have our pipe, which is coming up to our supercharger section right here. Now, this one's a little bit different than some other situations you might see because this is actually an injected engine. However, it is not injected at each cylinder. Instead, what we have is a single point of injection, which is injected directly into the supercharging chamber. And down here is where we have our throttle plate, which is going to regulate airflow into the engine. Now we have a injector controller, which is controlling the fuel flow. We don't need to cover that right now. We're just focused on the supercharger itself. But you can see the housing back here. Our injector's right here. Airflow is going to come up. It goes down into the center of our impeller. It's going to get slung out against the diffusers out into this outer track. And then we're going to see it follows this intake manifold portion, which travels through the sump, and then we go to each one of our individual intake pipes. Now, one of the reasons that you can get away with direct injection like this is because even if it's a supercharger that provides boost, it still has the ability to act as a distributing impeller, which means if we shoot fuel into it, then that fuel is going to get effectively blended up by the impeller and evenly distributed out to all these cylinders. Now, in this case, it's a little bit different than what we would see on the 985, which we'll take a look at in a minute, because we're traveling through a single point of exit from the supercharger going out to our different intake pipes. So really, this is one fuel charge that's getting distributed out here where the pipes start to branch off. Now, on the flip side, if we take a look at the 985, which is genuinely a distributing impeller, it works a little bit different. Now, this really doesn't provide any appreciable amount of boost. It produces a little bit of boost, but not a real appreciable amount. But what you can see as I look in here, grab a flashlight so it's a little bit easier to see. What you'll see as I look in here is these intake pipes, which are coming out of the supercharger section. Now, that supercharger section is being fed down here by our carburetor. Carburetor goes up into the supercharger. Voila! Again, same kind of flow down through the center of the impeller, but instead of going through a single exit point, that fuel coming from the carburetor is instead blended up by the distribution impeller, and it gets sent through each one of these 9 intake pipes in order to distribute fuel. So kind of a cool system. Works pretty well. Now, again, it doesn't necessarily have to produce much boost, but it does help us to get a more even distribution of fuel out to all of these cylinders, especially on a big radial engine like this. Anytime we talk about supercharging an engine or producing boost, effectively we're talking about an engine that can produce manifold pressures above 30 inches of mercury or above standard atmospheric pressure. That's ultimately what we're talking about. With supercharged engines, they're drawn off of the crankshaft, so rotational speed from the crankshaft is going to turn the supercharger impeller, which in turn is going to compress air as it enters the intake manifold. Now, one key with turbochargers versus superchargers is that superchargers will compress air after it passes through the carburetor. Turbochargers compress air before it passes through the fuel metering system or carburetor. So that's ultimately what we're looking at. The other main difference being is that with a supercharger, right, as we see with this graph right here, for what we call a ground boosted engine, which is an engine that can produce in excess of 30 degrees of mercury from sea level up to its critical altitude, the aircraft, as we increase power and we're at low altitude, we're going to produce the most manifold pressure that we can. However, as we start to increase our altitude, we are going to lose power output because we are seeing less dense air as we get higher up. Now, compared to a normally aspirated engine, we're still far in excess of what that can do. And really, this is why we developed superchargers in the first place, was to be able to fly higher. That's what we started developing them for. That's what we still use that technology for a lot. Now, in a lot of cases, as we started to diminish the effect, our supercharger can only turn as fast as the engine is turning. So even at full power, we couldn't get to turn any faster. That would be all we have. We're just on that single slope. Eventually, came up with the idea of having shiftable superchargers. So you'd have effectively a planetary gear set that could be shifted, so you'd have high blower and low blower. So you'd be on low blower as you increase altitude from the ground. After you reach the critical altitude for low blower, you would shift into high blower, and we get a much faster rotational speed that would give you a higher operation altitude, but we'd still see that critical drop-off over time. Now, the big key with a turbocharged engine is there are two kinds. One can produce boost from the ground or from sea level up to its critical altitude when it can no longer spin fast enough to maintain atmospheric pressure in the manifold. We refer to that as a ground-boosted turbocharging system. On the other hand, we have others that are referred to as a normalizing turbocharging system that are designed to maintain sea level pressures all the way up to their critical altitude. So the beauty of a turbocharger is it can be regulated so that it can spin faster or slower, somewhat independent of the rotational speed of the engine, which means we can produce consistent power output at any altitude all the way up to the critical altitude of that turbocharger. Now, as we take a look at a turbocharger, effectively all it is a cute little self-contained jet engine minus the fuel burning portion of it. Instead of having the combustion take place inside the turbo housing, what we have is a turbine, which is spun by exhaust gases, and then we have an impeller on the other side that compresses air that's entering the intake system. Now, the area between the outlet of the turbocharger and the throttle plate, or the fuel metering system, is referred to as the upper deck. Anything past the throttle plate out to the engine is referred to as the intake manifold. Upper deck pressure will always be higher than our intake manifold pressure. The reason being is that turbocharger is producing boost at the output, and that in turn is going to be regulated by the position of the throttle plate. Something you'll notice, though, is that turbochargers are fairly simply constructed. Part of that is because if we have too much weight or too much complexity, there's a good chance that it is going to overheat and come apart. In most cases, a lot of turbochargers can spin in excess of 100,000 RPM, which is pretty stinking fast, which moves us on to the lubrication requirements. Now, one of the keys with lubrication in a turbocharger are these bearings right here. These are actually floating bearings. They aren't pressed into the casing. So what happens is as we have oil pressure coming through the inlet, it is going to pressurize these bearings. So it'll pressurize both the layer between the bearing and the housing, and it will also pressurize the layer between the turbocharger rotor and the bearing. So we have a nice little film of oil on either side. It also allows that bearing to rotate at a slower speed than the turbocharger rotor is spinning as well. So in effect, we're getting more out of the same job with lubrication, so it keeps those bearings lubricated. It also has the ability to come into contact with the rotor, which is taking a considerable amount of heat from the turbine side. It can conduct that and take it out through the oil outlet. So our lubricating oil both lubricates the bearings in the turbocharger. It also can remove heat from the turbocharger housing, and this is going to be fed from the regular engine oil supply in most cases. There's a notable exception to that, but we'll probably talk about that when we're actually in lab. Now, if we look at a basic turbocharging system, it's pretty simple. All we have is exhaust gases, which are flowing to our turbine and exhausting through the exhaust pipe, which in turn spins the compressor, which draws air in and sends it back into the engine. Now, that's very simple, but there's no way of regulating this, so ultimately it's going to cause this turbine to overspeed and result in what we call overboost, which is very damaging to all the parts on the engine. So, in order to incorporate some regulation, we can use what we call a wastegate. This wastegate here is installed in parallel to the exhaust system. So we have exhaust gas that's flowing through the turbine section and out the exhaust tailpipe, but we also have exhaust gas that can flow through the wastegate and out the exhaust pipe. The idea is that we have a spring inside our wastegate controller which turns this into a normally open position. when this wastegate is open, it allows exhaust gases to bypass the turbo and therefore slow down the speed the turbine is rotating. However, when we build up oil pressure in this wastegate actuator, it forces this butterfly valve closed and forces more or all of the exhaust gas to flow through the turbine, therefore spinning it faster and faster, which gives us more compression going through the compressor side. Now, the way this works is very similar to the way that a propeller governor works, in that as oil pressure enters in to this wastegate, we can restrict over here, far away, if you can picture that out, we can restrict the flow of oil exiting that wastegate. So the more we restrict it, the more pressure is going to build up in that wastegate and it's going to push that piston in. However, if we relieve the restriction, so if we have a metering valve, whatever it is, if we relieve that restriction, then it's going to allow oil to flow out at a greater rate. Then the return spring is going to overcome the oil pressure and the wastegate can open back up. Very simple mechanism, but very reliable. Now, in the instance that we don't have a wastegate controlling it, we still have one way of controlling our output, and that is using an adjustable wastegate valve restrictor. Effectively, it's something that's set on the ground, and we have a pressure relief valve in line with the compressor to make sure that the system doesn't overpressure. All that happens is this valve gets set up as a restrictor for maximum output at the critical altitude of the engine. As a result, that's the only variation we get. So the turbine is going to spin faster and faster, and the only thing that protects this system from overpressure is this pressure relief valve that will release additional upper deck pressure as necessary. The next part gets a little bit complicated because we start talking about controllers. So I'm going to try to break this down as simply as possible. If you need to rewatch the video, well, that's why it's on a video. So let's dive into this. In a very basic system, this is something you'd see typically with a Teledyne Continental motor. They like this system quite a bit. And there's a couple familiar parts here. We have our wastegate actuator over here. And what you can see is we have oil entering from the engine and then exiting to our controllers. And it's eventually going to go back to the oil sump, since it's all part of the same system. What we have over here are two controllers that are installed in parallel. We have the absolute pressure controller and we have the pressure ratio controller. Now, the job of an absolute pressure controller is to monitor the upper deck pressure before it heads to the throttle valve and into the intake manifold. Effectively, there is a bellows that's charged with nitrogen on the inside that is sensitive to a specific preset pressure inside the upper deck. So effectively, it is controlling the upper range that the upper deck can have in terms of pressure coming from boost. So what happens is as the throttle is advanced, we are going to push more exhaust gas through this system and through the turbine. Now, the wastegate is normally going to be open during start, and it will continually close as needed to maintain the higher upper deck pressure that we need. So as long as our upper deck pressure is beneath the maximum level, right, so we'll indicate this here, our upper deck pressure is getting fed into this controller, and so long as it stays underneath the maximum level, then this pressure controller is going to stay closed with this little metering valve, which as a result is going to build up pressure in our wastegate actuator and close the wastegate, which gives us faster speed. As the turbine continues to spin faster and faster, we will build up upper deck pressure. As we approach and reach our maximum upper deck pressure, we have a pressure relief valve to protect it from overpressuring, but as we approach that high pressure is going to act against the bellows and is going to push this little metering orifice out. Once that orifice is pushed out, it's going to allow oil to flow at a faster rate through the absolute pressure controller and exit into the oil sump. What that does is it reduces the oil that's built up in our wastegate and allows the butterfly valve to open, which in turn is going to allow exhaust gas to bypass and turn that turbine slower, which reduces the amount of boost we're producing. Now, that is a simple system. What we have in addition to help protect the system is the pressure ratio controller. Most modern turbochargers are capable of producing extreme amounts of boost, and also capable of getting the aircraft to fly above its critical altitude, at which point in time we could start dealing with issues just from fuel injection, from different dynamics of the engine itself, up to the point where the amount of heat that we see coming through the engine could potentially cause an issue for things like detonation. So we have to limit the aircraft to its designed critical altitude, and that's what the pressure ratio controller does. As you can see, it's linked up to our upper deck pressure, again acting on a bellows, but this time it's being referenced to ambient air pressure around. What that does is this bellows is designed to keep a balance between the amount of pressure that's in our upper deck and the amount of atmospheric pressure. Effectively, there's going to be a ratio of around twice as much pressure in the upper deck as compared to ambient air. That's the magic number. So as we start to get outside of that ratio, if we build up too much pressure in the upper deck, it's going to push down on this bellows, overcoming pressure from ambient air, and it's going to open up this restrictor valve, which again allows excess oil flow back to the sump. So effectively what we have are two different controllers installed in parallel. Either controller has the ability to force the wastegate actuator to open up and allow exhaust gas to bypass out through the tailpipe. Now I mentioned this is pretty typical to Teledyne Continental. There are two additional controllers that we didn't have a chance to talk about. We talked about our absolute pressure controller, the APC, which is just going to monitor pressure in the upper deck, and it's all based on how that bellows is set up on the inside. On the other hand, we have a variable absolute pressure control. What that does is effectively the same job. The only difference is we have a throttle controlled cam over here. All that cam does is increase pressure pushing against this restrictor valve, right, which is going to change this balance with the aneroid up there. And all that throttle controlled cam does is create basically a scheduled boost range for any given throttle position. So it provides control over the turbocharger output at all throttle ranges, all the way up to maximum throttle, and it's directly linked in. When you're looking at these from the outside, the easy way to tell if it's a regular APC or a variable APC is that throttle controlled cam. Another version that we'll talk about is the sloped controller. It's a relatively newfangled, and when I say newfangled, I mean like sometime in the 60s. Continental started using these, and effectively what it has is the ability for one controller to sense the pressure from the upper deck as well as pressure from the atmosphere around, and it has a diaphragm that acts against each other. So effectively what it's doing is controlling both the full throttle performance of the turbocharger as well as the partial throttle performance of the turbocharger. You can kind of look at it as combining the job of both components in the system that we just referenced. The only main difference is, as opposed to being completely self-controlled, we have an adjustment screw right here. So the way that's set up is the aircraft is brought up to temperature, the engine is run up to full power, we see how much boost is being produced, and we read the manifold pressure reading, and depending on what the manifold pressure reading should be, given the atmospheric conditions, we can make adjustments with this screw to adjust what our maximum manifold pressure output is going to be. It's a lot, so if you need to take a second to pause, please go ahead, but otherwise we'll keep moving along. In this case, we're going to take a look at something that is typical of the Lycoming system, and this is an example of what would be probably considered a normalizing turbocharging system. And effectively, most of the components are going to be the same. We still have our wastegate and wastegate actuator. We have exhaust gases flowing through the turbine and in parallel through the wastegate. We have our air inlet that's feeding the upper deck and the intake manifold. Now, something that's interesting to notice here is we have a density controller and we have a differential pressure controller. The density controller is a little bit different than what we're used to seeing with the Continental systems, in that the density controller is only going to regulate the position of the wastegate at wide open throttle. But the added benefit it has is it has this nitrogen charged bellows, which allows it to compensate not only for the pressure in the upper deck, but it can also compensate for the changes in density of the air moving through the system according to temperature. So as the temperature increases or decreases based on output of the turbocharger, atmospheric conditions, it is going to regulate based upon that, but also upper end pressure. So the density controller controls our top end with the turbocharger output. For all positions other than maximum output, we have this differential pressure controller. And the way that that works is for all positions of the throttle, remember, this throttle plate acts as a restrictor. So as we have a lot of pressure built up in the upper deck, this differential pressure controller is going to limit the amount of air that can move through, and so we can create different pressures on the other side of the throttle plate in the intake manifold. Now, what this monitors is pressure in the upper deck and pressure in the intake manifold. When we have a high amount of pressure and a low amount of pressure between the two, then this is going to sense that difference and it's going to cause a movement in the restrictor valve here, which allows the wastegate to open or close to try to bring our upper deck pressure and intake manifold pressure closer together, to try to equalize those as much as possible while still maintaining a head of pressure in the upper deck. On the other hand, it also has the ability to limit what we call bootstrapping. Bootstrapping is commonly confused with overboosting because it could potentially result in overboosting, but realistically, bootstrapping is whenever we have a change in turbocharger output without a change in throttle position. So as the aircraft is flying, we are going to have a somewhat variable output from each cylinder just because of temperature, because of completion, of combustion. There's any number of factors that can change that. Anytime the strength or quality of our exhaust gases flowing through the turbine changes, it's going to make the turbine spin a little bit faster or a little bit slower. As a result, that is going to change our output to be a little bit higher or a little bit lower, which is going to cause those transient changes in manifold pressure because of the change of the output from the compressor. We refer to that as bootstrapping. Because this differential pressure controller can sense pressures on both sides of the throttle plate, if we do have a change suddenly in the upper deck pressure as opposed to what we see in the manifold, it can regulate that wastegate and cause it to open or close to match those pressures. So it helps to eliminate bootstrapping on a turbocharging system. But again, the system is fundamentally the same. We have two controllers that are limiting the amount of oil flow from the wastegate actuator, and it goes back to our engine oil sump right there. Relatively straightforward. Something that trips up mechanics pretty frequently is trying to figure out where in the world all of the components and controllers for a turbocharger are on the engine. It's one thing looking at a schematic on a page going, okay, great, that's where it is. It's a little bit tougher when you actually try to find it on the aircraft for an inspection. So I'm going to show you my tried and trusty method here for identification, which is basically kind of the same way you untangle a extension cord or a knot. You just start pulling at one thread and keep following until you get to the end of it. So turbocharger is going to be driven by exhaust gas, so what I like to do, follow the exhaust system back to the turbocharger. So right back here, we have our exhaust header coming off of one side, and we're coming, boy, look at that, right to this big old turbocharger. Now, one thing you'll notice is it's not where it is on every other installation I've seen, but we're going to have a wastegate somewhere on the exhaust side of this turbocharger to regulate airflow, and by golly, there it is. Here is our wastegate, and what this is going to do is it's going to regulate how much exhaust is allowed to spool through this turbine section of the turbocharger or how much is allowed to exit. This cover plate would not normally be in place, especially since that's just a paint lid. It actually is not supposed to be there. Anyway, normally exhaust would come out through the center portion bypassing the impeller wheel on this the turbine wheel on the turbine side here, and that is what would power our turbocharger. So here's our wastegate controller. Remember, we have a spring-loaded valve in here which is going to move back and forth, and that is controlled by oil pressure. So we have two lines. This is going to be oil pressure. One is going to be oil in, one is going to be oil out. Now, the way you can tell which one is oil in is because it is the line that goes directly to the engine itself. On the flip side, we have up here, where our upper deck is, an oil line that runs up to, oh, here we are. This is our absolute pressure controller. So as oil flows through, it's going to flow into this chamber on our wastegate, and then it's going to continue to flow up to our controller. This controller is what controls the leak rate of oil coming from the wastegate, going back to the engine return through this line. It controls basically how fast oil can leak out of this wastegate, which ultimately is going to control the position of the wastegate. So the more wide open this is, the more oil flow, which means the wastegate is going to be allowed to be more open, which reduces the amount of boost we get. On the flip side, as this seat is closed, then our oil flow is restricted. We build up oil pressure in our wastegate controller here, forces the wastegate closed, and we get faster rotation on our turbocharger. Now, as I look at this, I can tell you right now that it is a variable absolute pressure controller, VAPC. Why can I say that? Well, when I look at our throttle linkage right here, you'll notice there is a nice, neat little cam up at the top. You can see that moving back and forth. Remember, the only big difference between an absolute pressure controller and a variable absolute pressure controller is the VAPC has a cam that's linked to the throttle so that we can effectively force the scheduling or boost amount based on throttle position rather than just what the pressure controller is sensing. So as we advance the throttle, it's going to create more spring tension against that aneroid and poppet valve. It's going to make it harder for it to unseat, which as a result builds up more oil pressure for us. Everything works. So there are our two controllers. We have the wastegate and the thing controlling the wastegate. And we really don't have any other controllers on this, and I can verify that by the fact that there are no other systems plumbed in that are going to change how oil flows out of this wastegate controller. So this is our only line out, and it goes through this controller right here. If we had another controller in parallel, it would function in parallel so that if it needed to change the amount of boost being produced, then it could take out that oil pressure. Now, on the flip side, this is not a sensing controller, but rather it's just a pressure relief valve. So up here would be considered our upper deck section, right? Anything prior to the throttle valve is going to be considered our upper deck, which means if we start building up too much pressure in the upper deck, if the turbocharger is over boosting, it's going to unseat this pressure relief valve, and we're going to allow pressure to be sent overboard and protect the system. Everything downstream from the throttle valve is going to be considered our intake manifold. Right here we have our aftercooler. Remember, intercoolers are only in between stages of boost. If it is after a device that is providing boost, namely a turbocharger, then this is an aftercooler. The aftercooler feeds our intake manifold over here, which is going out to our cylinders.